Okay, welcome to the second group of topics from Unit 3, okay, or Topic 2, Unit 3. And in this class, we're going to be talking about the Compton effect, momentum of photons, and deBroglie, or deBroglie wavelength, to be specific. Okay, so we've already talked about the energy of photons and how the energy depends on the frequency or the wavelength. We've talked about the photoelectric effect, where incoming photons that are about to strike the surface of the metal must have a sufficient energy to bump electrons off in order for the photoelectric effect to occur. And that minimum amount of energy is called the work function. So what we're going to do now is we're going to take a look at some other things that kind of led from that research that was carried out by people like Albert Einstein and Max Planck. So we're going to talk about Arthur Holly Compton. And one day he decided, for some reason, he was going to shoot some X-rays at a piece of metal, a piece of thin metal foil, like a piece of tin foil, just to see what would happen. Because Compton had it in his head that if photons can knock electrons off the surface of a metal, then they must have momentum. Okay, so what he did was he developed this experiment where he shot high energy X-rays at a piece of foil. And what he found was after the target was struck, he noticed that other X-rays came out the other side, but the X-rays were changed. They actually had less energy. And he could tell that because they had a longer wavelength. And remember, Planck and Einstein had already said that energy was inversely proportional to the wavelength. So because they had a longer wavelength, they must have had less energy. So the energy they lost ended up going into some electrons that got ejected. So very similar to the photoelectric effect in a way, only in the photoelectric effect was a little bit different. Just a little different. This time we're using, first of all, X-rays, and the X-rays got re-emitted on the other side of the foil, and electrons got ejected as well, similar to the photoelectric effect. Anyway, we call that particular phenomena the Compton effect, because it was discovered by Arthur Holly Compton. Anyway, so what you will notice if you look at the diagram here is that not only do the high energy X-rays strike, but when the lower energy ones come out the other side, they don't come straight through. They bounce off at an angle. In fact, they don't even bounce back this way. Most of them go this way. So what's happening is these lower energy X-rays are colliding with electrons and bumping them out. Okay, very similar to what was happening in the photoelectric effect. Anyway, the word scattered is used for these because these ended up being scattered all over the place. And he had a detector over here. He basically mounted a screen all the way around the back here that would detect where those photons, those lower energy X-ray photons, would end up. Okay, and we use scattering because they're kind of deflected all over the place. So what Compton decided to do was he was going to use the laws of conservation, specifically conservation of energy and conservation of momentum. So first of all, energy. The energy of the incoming X-ray photon, energy of X-ray, would be h times f, h times frequency, or hc over lambda if you prefer. And the energy of the scattered X-ray would be E scattered equals hf scattered. And remember that the frequency of the scattered one had to be less than the frequency of the original X-ray photon because the scattered ones had less energy, right? Conservation of energy. They couldn't have more. You don't get something for nothing. They had to have less. So since the scattered electron has a mass, because an electron is definitely a particle, we can say its energy is just kinetic energy, which is a half mv squared. So this is what Compton came up with. This was his equation. And this is essentially how he measured the wavelength or frequency of the scattered X-ray photon. Okay, because he could measure the energy of these electrons, and we've talked about that before, in the photoelectric effect, there was a method for doing that. So we can measure that. We know what the frequency of the X-ray machine was, so that would tell us what the wavelength or frequency of these are. But Compton went a step further. He said that if this occurs, then the law of conservation of momentum would also apply. So Compton is best known for his contribution to the idea of photon momentum. Okay, Compton really believed that photons did have momentum. So you may remember from Physics 2204 that momentum, or P, equals m times v. P equals m times v. P for momentum. Okay, so what he said was, Einstein had already published a paper talking about the special theory of relativity. And in that paper, Einstein had talked about a energy mass equivalence. Okay, so what he said was E equals mc squared, probably one of the most famous equations ever in physics. But anyway, what Compton did was he rearranged it as this, m equals E over c squared, and he said that was the mass of the photon for purposes of momentum, or that was the mass equivalence anyway. Okay, it's not actually a mass, but it has a mass equivalent according to Einstein. So what he did then was he substituted this into his definition of momentum that we already knew about. Momentum equals mv. So now the mass is E over c squared, so we've got momentum equals E over c squared times v, which is what we've got here. But remember, for photons, photons travel at the speed of light. So the speed v is actually c. So instead of saying EV over c squared, we can say EC over c squared. And when that happens, we can do this. We can actually cancel this c with one of the c's on the bottom, and we're left with momentum equals E over c. Momentum equals E over c. But to go one step further, Planck had already said that this was true, or at least it was the theory that it was true. E equals h times f, or hc over lambda. So Compton took that for the energy, plugged in hc over lambda, and again the two c's will cancel, and you're left with this. P equals h over lambda. That is Compton's equation for photon momentum. That formula is on the formula sheet that you get with your public exam. And that's what it's used for. It's used to calculate the momentum of a photon. A single photon of light. All right? And Compton said that if these particles are colliding like this, if electrons are being bumped off, there had to be a collision, and if there's a collision, there's momentum involved. So this is what Compton came up with to calculate the momentum of these photons. Okay, so that's Compton's equation. Now, then right after that, along came another guy by the name of deBroglie, or deBroglie, depending on how you like to pronounce it. And he went one step further. He took Compton's equation and rearranged it. So what he said was, if waves, photons that travel like waves, if a photon could have momentum, which is primarily a particle property, so if a wave could have momentum, then why can't a particle have a wavelength? Okay, maybe particles and waves are much closer together, or much closer to being the same thing than we initially thought. So deBroglie said this. After Compton showed that electromagnetic radiation, photons, showed some properties of mass, such as momentum and energy and things, deBroglie wondered that maybe mass might have a wave property of wavelength. So what he did was he took Compton's equation, which is P equals h over lambda, this guy right here, and he rearranged it. He just said, in that case, lambda, wavelength, would be h over p. But remember, momentum is mass times velocity, so he put mass velocity back for p, and he ended up with this. This is known as deBroglie's equation. That one is not on the formula sheet, but all you have to do to get that one is to substitute mass times velocity in place of the p in Compton's equation. And that's deBroglie's equation. Okay? And that's used to calculate the wavelength of a particle. Now, that might seem a little absurd, but it was later discovered, and this kind of held up deBroglie's hypothesis. It was later discovered that electrons, when they were beamed through a narrow opening, would show the same interference patterns that light showed when it was shone through a narrow opening. So, if things are interfering, it must be moving as a wave. So maybe particles did have a wavelength. And like I said, there is lots of evidence to support deBroglie's hypothesis. So let's take a look at some of the things we can do with that. Okay, there are a number of multiple choice questions that you could be asked. So here's the first one, deBroglie wavelength. deBroglie wavelength of this is the mass of the person. This is the wavelength. Now, deBroglie wavelengths, typically we use those with very, very small objects traveling at high rates of speed. Small objects like protons and electrons and things like that. It's a little absurd to use it with a 50-kilogram person because the wavelength is so small that it's virtually unmeasurable. I mean, look, 10 to the negative 37 meters, when you think about it, is actually a bit ridiculous. But, nonetheless, if it works for small objects, then reason would say that it works for larger objects too. So there's deBroglie's equation. The h is the same constant we used before. It's Planck's constant. So 6.626 times 10 to the negative 34 divided by the mass, which is 50, and the speed. Oh, hold on now. We have to rearrange this, don't we? We actually have to rearrange this equation. We actually have to say that v, let me backtrack here just a little bit. Let me move this down. There we go. We actually have to rearrange that so that speed equals h over m lambda. Okay, we can actually do that. Okay, whenever you're trying to find something that's on the bottom of one side of the proportion, swap it with the top on the other side. It's as simple as that. It's a very easy rearrangement. Anyway, the wavelength is given 4.4 times 10 to the power of negative 37. And the answer, when you do that calculation, is 30. Now the problem is 30 only has one sig fig. So we write it as 3.0 times 10 to the power of 1. Now that's pretty fast for a person to be going too, isn't it? You're running at 30 meters per second. That's over 100 kilometers per hour. So the numbers here are kind of a little bit out to lunch, but anyway. Second question on the page. Which of those characterizes a photon of light? Okay, so we've talked about two things now. Planck said that a photon had energy. Planck and Einstein said that. And now along comes Compton and says not only that, but a photon has momentum as well. So the answer is both energy and momentum. Both energy and momentum. According to Einstein, Planck, and Compton, it has both. deBroglie wavelength of a neutron. So we use this equation again, h over m times v, and the h is the same constant that we've used, Planck's constant, which is on the data sheet, by the way. Now, we're not given a mass, but it does say it's a neutron. And according to your data sheet, the mass of a neutron is, and it's given there, it's written there as m subscript n, mass of neutron. 1.675 times 10 to the power of negative 27 kilograms. That's the mass of an individual neutron. and we're told it's traveling at 5.00 meters per second. That equals, when you do that calculation, 7.91 times 10 to the negative 8. So there's your answer right there. Okay, and a lot of those are very similar. Okay, that particular equation comes up a lot. This next one, this is an example of Compton's equation. P equals h over lambda, which can be rearranged as lambda equals h over p. Okay, we know h because it's a constant, 6.626 times 10 to the negative 34, and we know p because it's given. That's momentum, 5.60 times 10 to the negative 27. Do that calculation, and you will get 1.18 times 10 to the negative 7, right there. Then the next one, okay, very similar, only this time it's the wavelength of the matter wave associated with an electron. So that's the deBroglie wavelength, in other words. So wavelength equals h over m times v. The h is the same. The mass of the electron, you look up on the data sheet. It's given. Okay, I'll write it down here for you. But it is given on the data sheet. It's there as me, mass of electron, and it's 9.11 times 10 to the power of negative 31. And it tells us this electron is traveling very fast at 2.5 times 10 to the 7. In other words, it's traveling at 25 million meters per second. That's pretty fast. Anyway, the answer to that is 2.9 times 10 to the negative 11, or choice A. The next one says we got a photon with an energy E0 strikes a free electron. So let's use energy conservation. Energy before equals energy after, which I usually write as E prime. E before equals E after. So the energy before is just the photon. The photon strikes an electron and knocks it loose, strikes a free electron, gives it some kinetic energy. And in the process, it now has an energy of E afterwards. So that's what it is. There's before, there was just the photon, and afterwards there's another photon with a different energy, and there's an electron with some kinetic energy as well. So since I'm trying to figure out what this guy is, all I got to do is move the E over and subtract it, and I've got the kinetic energy of the electron. So the answer is C. Just conservation of energy. Really what that is Compton's equation, right? That's Compton's energy equation for photons. Anyway, moving on. Frequency of a photon of light with the momentum of this. Well, remember, momentum equals h over lambda. Okay? That's what Compton said. So therefore, we've got lambda equals h over p. So we do that calculation first, plug in h, which is 6.26 times 10 to the negative 34, Planck's constant. Divide that by the momentum we're given, and we get this as the wavelength. There's our wavelength, 2.366 times 10 to the negative 7. Now be careful, because that's not the answer. That answer's there, but that's meters. That's the wavelength. That's not the answer. So it's not that one. Be careful. It asks for the frequency. And remember, frequency equals c over lambda, universal wave equation. So we take the value of c, which, remember, is 3.00 times 10 to the 8. That's on the data sheet. Divide it by 2.366 times 10 to the negative 7. And you will get the correct answer, which is this one, 1.27 times 10 to the 15. So like I said, be careful, because there are other answers there that take into account common mistakes that people make. So you really got to watch yourself. Next one, the mass of an object thrown with a speed of 45 meters per second. Well, again, It's de Broglie wavelength, so the formula is this. There's the de Broglie wavelength equation. We rearrange it so that we have mass equals, and we can swap the wavelength and the mass, right? Top and bottom. So I got h over lambda times v. V times lambda. And plug in the numbers. We're given everything, right? We're given the v. We're given lambda. H is a constant. So when you put all those numbers in and do the calculation, there's the answer you'll get. 0.044. Okay, if you don't believe it, go ahead and try it. Plug the numbers in. And the next one there, the Broglie wavelength of a proton. What is the speed? Well, again, same formula. Lambda equals h over mv. This time, though, I'm asked to find the speed, so I say v equals h over m lambda. There you go. So what we do is you plug in those numbers, and again, I'm not going to write them all out because you've given them all. This is mass of proton, which is like that on your data sheet. You look it up, and the mass of a proton is 1.673 times 10 to the power of negative 27. You're given the wavelength. You know what h is because it's a constant. Plug all those in and do the calculation, and you get this, 0.711, which is actually 7.11 times 10 to the negative 1 when you change it to scientific notation. And you're going to find they do use scientific notation most of the time in the answers, especially when there's a broad range of numbers like this, everywhere from -1 to an exponent of -27. That's a pretty big range. So they typically do use exponential notation, scientific notation, that type of thing. Anyway, next one. This one is a level 3. And I do try to throw in a scattered level 3. Okay, and what you got to remember in this one, this is tying what we did in Unit 2 with Unit 3. Okay, or also what we talked about with, remember EV stop? Energy, E, is equal to EV stop. Remember that? But that's the same thing as Q times V. Right? Q being the charge on the particle. E is the charge on an electron. Q is the charge in general on any particle. Okay, but we also know that the energy of a photon is equal to hc over lambda. Okay, and in this particular case, if photons have energy, then any particle we could measure the energy if we knew the wavelength. So we could actually say this. We can actually use this expression for the energy of any particle. So I'll just make the two of these equal. I can say Q times V, or V times Q, is equal to hc over lambda. But I'm trying to see what is the wavelength. I'm trying to get lambda by itself. So I swapped the top and the bottom, and I got lambda equals hc over qv. Okay, and that happens to be A. That's the way that one works. Okay, it's taking two things that you learned in two different parts of the unit and putting it together. That's what makes it a level 3. Two seemingly unrelated things that actually are related. And then the last multiple choice there says, which property would the Compton effect describe about photons? The Compton effect was all about momentum. The Compton effect is all about the momentum of photons. That's what Compton was trying to prove in his experiment. He was trying to prove that photons have momentum. So there you have it. Last multiple choice. What did Compton discover after bombarding electrons with high-energy photons? Well, again, remember, it was all about the momentum. He discovered that a photon's momentum depended on its wavelength. That's what he found. All about the wavelength. A. Okay, don't get fooled by B. A photon with a shorter wavelength can be ejected. Well, a photon with less energy was ejected. But less energy means a higher wavelength, not a shorter one, a longer wavelength. Electrons and positrons come in pairs. That's totally irrelevant to this. That's in nuclear reactions later on. And electrons can be split into smaller particles? No, they can't. All right, so that's that. Now, very rarely are there any long answer questions on these particular topics, but every now and then something sneaks in, so let's take a look at some. This one, for example. Two subatomic particles with very different masses have exactly the same de Broglie wavelength. Explain how this is possible. Okay, now that's actually a pretty easy question. Okay, because de Broglie wavelength doesn't only depend on the mass, does it? De Broglie wavelength depends on three things. Depends on Planck's constant, h, which is a constant, so that's not going to have any effect. It also depends on the mass and the velocity. So if they have very different masses, then it stands to reason that they would also have very different velocities, right? So here's de Broglie's equation. Lambda equals h over mv. Okay, and just getting to that point, look, was worth 2 out of 3 marks, believe it or not. Okay, therefore, if the wavelength is to remain constant and the masses are different, then the speeds of the particles have to be different as well. For example, if one particle is twice as much mass, then the speed has to be half as big in order to balance it out, in order to still have the same wavelength. Okay, so pretty easy question when you think about it. Try this one. What is the de Broglie wavelength of an electron with a kinetic energy of 2.4 electron volts? Now that one's a little different. Okay, first thing we have to do is say Ek equals a half mv squared. So if we want to know de Broglie wavelength, the first thing we've got to do is we have to figure out how fast that electron is going. And that's easy enough to do. We can say V equals, rearrange the equation, the square root of 2 Ek over m. Work it all out. You get 9.19 times 10 to the power of 5. There's the speed. Then once you know the speed, you can use de Broglie's equation to find what I should say lambda. Sorry about that. That should be a lambda right there, not a p. Okay, lambda equals h over mv, de Broglie's wavelength equation. Plug all the numbers in. The answer is 7.9 times 10 to the negative 10. Just a two-step equation, that's all. Very easy. Last one. What is the frequency of photons with a momentum of? So again, first thing you have to do is find the wavelength of those photons. Okay, you have to find the wavelength of those photons, and momentum equals h over lambda. Okay, this is, I'm not sure what's done here. I'm trying to figure it out now. Anyway, here's the better way to do it. Okay, momentum equals fh over c, which basically rearranges the equation. Anyway, you get the same answer either way. Same answer either way. What they've done here is they've skipped a step. And again, I just took this from an old public exam. Okay, what they've done is this would equal a wavelength first, and then you change it into a frequency by doing this. Frequency equals c over lambda. Okay, that's where this number came from. Okay, and this one here actually puts all that in the same step. Okay, so c over lambda is equal to f. So that's where that equation comes from. Okay, which is what gives you that answer. So either way, what you can do is you can find the lambda first, then change it to a frequency, and you get that answer. Or you can do it all in one step, and you'll still get the same answer. But like I said, those types of questions, very rare on part 2 of the exam. Very rare. There's other things there that they can ask that are usually just multiple choice questions. In fact, one of the multiple choice was actually exactly like that question. One of the multiple choice that we just did a couple of minutes ago. So, there you have it. So that concludes topic number 2 from Unit 3. Topic number 3 from Unit 3, which is the next one, will be all about the Bohr atom, B-O-H-R. The Bohr model of the atom, and some of the calculations we can do involving that. So keep on studying, work hard, and you'll find the public exam just fine.